Good afternoon.
Good afternoon.
Good evening to one and all. I am Himanshu Thakur from Team IEEE BVMSP, and I welcome you back to the fourth session of the International Tech Conclave, ITC. Before going ahead, participants kindly keep a note. Certificates will be provided to only those who attend all the sessions of ITC. I request to like the videos and also subscribe to the channel. At the same time, if you have any queries for the speaker, you can use the chat sections and our moderators will forward it to the speaker. Today, for the upcoming session, we have with us Mr. Stanislav Eroshenko, sir, who would be talking about machine learning for solar energy forecasting. Now, I would like to call Dr. Mukesh Shimpi, sir, Associate Dean in R&D at BVM Engineering College, to take the proceedings further.
Good afternoon. I, Dr. Mukesh Shimpi, R&D Coordinator at Birla Vishwakarma Mahavidyalaya. Welcome all the participants to the International Tech Conclave 2020. Now I welcome our speaker, Mr. Stanislav Eroshenko, of our today's session on machine learning for solar energy forecasting. He is a senior lecturer, leading engineer in Ural Power Engineering Institute, Ural Federal University. His specialization is in power engineering. He is having 10 years experience in teaching. He is having scientific community membership in Russia and involved in many R&D projects. He has published more than 25 papers in reputed high-index journals like Web of Science, Scopus, and etc. He has published 4 books and participated in more than 30 international conferences. He is a leader and developer of the module Power and Electrical Engineering within the framework of Ural Federal University educational program. We welcome you, sir. Now I hand over the session to Himanshu.
I request Stanislav to please take over the further sessions. I request sir to unmute his mic. Thank you, sir.
Yeah, thank you very much. So I hope it's okay with video and audio connection. It's my great pleasure to introduce myself and the university that I represent. I'm from Ural Federal University, and my today's topic would be devoted to machine learning in solar energy forecasting. Well, actually, it's a project of my life, one of the projects of my life. And we have a very powerful research team at our university. And actually, there are lots of collaborations in terms of this project with other universities from all over the world, but the main ones are from India, from China, and from France. Well, let me firstly speak very briefly about the concept of today's energy sector. Well, according to the, let's call it public events, like SIG session, which was held in 2018, the power industry and the energy sector today is becoming more oriented towards digital technologies and towards the final customer. Yes, and the final customer, the load, becomes to play a more and more increasing role in the life of the energy sector. And today's energy sector is represented by such, let's call it novel phenomena, like overall distributed generation integration, development of renewable energy sources, cybersecurity issues, and big data applications, because there are lots of monitoring and control systems nowadays that are producing huge amounts of data, which can be used in a proper, practical way and produce very good results. The Internet of Things and the Internet of Energy, it's actually one of the greatest means oriented towards the final customer, and there are lots of novel services which appear in the energy markets and give the customers more opportunities in terms of the load regulation and their profits and benefits. Of course, a very big share of publications and a very big share of topics in the research community are devoted to smart grids. It's highly integrated grids with information technologies, which provide flexibility, reliability, and security of the final energy supply. Well, my today's topic is mostly devoted to renewable energy sources development. And well, maybe a couple of years ago, maybe 4 or 5 years ago, it was not so urgent, even for Russia, because we did not have too much renewable energy because of the climate. You know, the climate is quite severe. And according to the statistics of the recent years, so you can see it on the slide, starting from 2016, the installed capacity of photovoltaic power plants is growing rapidly. And actually, there are some strategic development plans and documents which provide us with the strategic goals of the share of renewable energy sources to be provided in the final balance of the fuels for the country. And in terms of renewable energy sources, let's call it wind, sun, hydropower, small hydropower. The total share should be for approximately 5% by 2024. Yes, and now we have the total amount of 1,439 megawatts of photovoltaic power plants, which are operated and integrated in the United Power System of Russia. Well, actually, if taking the the total installed capacity of the generation in our country, the total share is not so impressive. But anyway, taking into account the climatic and weather specifics of the country, all of these generation capacities are concentrated in southern regions of our country. And some of the regions are, let's call it, overpopulated with PVs. And for this reason, this produces some power system operation problems. So I will talk briefly about some power system impacts which are introduced by photovoltaic power plants. So this figure presents a share of the United Power System, which is supplied by 220 kilovolts power transmission lines, or transmission lines. And actually, there is a very big share of renewable energy sources allocated throughout the territory, and the total solar capacity is about 300 megawatts. Moreover, the total wind installed capacity is about 90 megawatts. So we have about 400 megawatts of renewable energy operated for this share of the power system. Actually, if speaking about the reliability and let's call it assurance of the current carrying capacity of the power transmission lines, it was always thought that we are to ensure reliable operation of the power system in the conditions of thermal power plant generation outage. And for this share of the power system, the typical outage of thermal power plant generation is one generation unit having the capacity of 250 megawatts. And now we have the scenario that the total installed capacity of sun and total installed capacity of wind together, they are higher than the united capacity of thermal power generation plant unit. And for this reason, there are actually some new power operation conditions which should be taken into account. And there are some new regulations and rules should be provided to ensure the maximum possible power flow for these power transmission lines. Because if we have unpleasant weather producing lots of clouds, maybe rain, we have a group reduction of the power produced by photovoltaic power plants, and this can exceed the maximum calculated generation outage for thermal power plant. Thus, it can provide the overloading of the transmission lines, which connect this share of the power system with the big power system of the country. And actually, on this slide, there are some diagrams providing the measurements of possible power production reduction of the photovoltaic power plants. And here we can see that these measurements are provided for these 220 power transmission lines. And we see the 100 megawatts reduction of the power produced by photovoltaic power plants for a 10 minutes period. Actually, photovoltaic power plants are one of the generation sources which have very low inertia. Yes, and the speed of power production decrease can be very high, and it could be hundreds of megawatts per second, maybe per minute, depending on the climatic conditions which occur. For this reason, the big share of photovoltaic power plants allocated throughout the territory of southern regions impose a very serious problem connected with the power system operation mode reliability insurance. And for this reason, some let's call it serious actions should be taken to ensure reliable power system operation and reliable supply of the final customers. Yeah, this is another region of our country having the photovoltaic power plant and the thermal power plant installed in the Orsk load center. And we see here that the transmission for transmission lines and the power flow for these transmission lines depends greatly on the transmission, depends greatly on the generation of the power at solar power plant. And it can be seen from these figures, because when we have daytime and the power plant, photovoltaic power plant produces a certain amount of energy, so we can see the fluctuations for the power transmission lines. And we see that the power flow for these transmission lines depends greatly on the amount of energy produced by renewable energy source. Well, actually, this mainly conditions the urgency of the problem of photovoltaic energy forecasting And well, when dealing with this problem, we find out that it's not an easy thing to do, because the power produced by photovoltaic power plants is highly stochastic, and it depends on a very big amount of external factors, mainly meteorological and weather factors, which cannot be easily predicted highly accurately to produce the reliable forecast of the energy for some period ahead. And if we speak about the physics of solar irradiation distribution in the atmosphere of the Earth, so we should take into account lots of factors. There is the ozone layer, while there are some water molecules in the air, and there are some clouds which consume the energy of solar irradiation in the atmosphere of the Earth. Moreover, if we have the angle, so if we do not have the direct angle of falling rays, so we'll have some energy losses too. Some irradiation would be reflected, some irradiation would be diffused, and all these factors are to be taken into account, because there is a very small share of useful energy which can be extracted from the total energy of solar irradiation. It's only the one side of the problem, because the second side of the problem deals with the photovoltaic plant itself. So we have different types of PV panels. They can be polycrystalline, monocrystalline, or amorphous. So we have a certain circuit connection at the solar power plant. So we have some converters, inverters, and they're highly nonlinear, and they produce fluctuating efficiency. So we have some alternating current side of the photovoltaic power plant. So we have losses in the power transformers and power transmission lines. We have some restrictions associated with external power system, and all of these criteria are to be taken into account when producing a forecast of the PV power plant production. Moreover, so if we take volt-ampere characteristics of solar power plant, we'll see that the amount of the power produced by the PV panel depends greatly on the level of solar radiation. So, and moreover, it depends greatly on the outside temperature. And it's surprising, but from the point of view of the ambient temperature, the best place to install solar power panels is the northern pole. But there we have very short sun day. For this reason, it's in the majority of cases, it's not too much efficient. But from the point of ambient temperature, we have to provide some coolant cooling for the semiconductors to make them work more efficient. Moreover, so if we consider the geometry of the sun movement in the sky, and we'll have a very complicated sinusoidal model giving us a basic knowledge about the amount of solar irradiation which can be usefully extracted for certain periods of time throughout the day. Well, if we take photovoltaic power plant forecasting problem, well, it is not firstly solved all over the world, of course, and there are lots of research projects devoted to this problem. And in the majority of cases, the models, the mathematical models, can be subdivided into adaptive, machine learning based. Some use analytical models, and some use mixed models because they produce, let's call it the golden middle between the adaptive methods and statistical approaches. But the general research community provides us with the following data, and which depends greatly on the perspective of forecasting. Because if we consider different problems, like very short-term forecasting is like intraday and intra-hour forecasting. If we consider short-term or middle-term forecasting, these problems are very different. and different initial data is required to succeed and to get the accurate result of photovoltaic plant energy production. And in my presentation, we mostly deal with short-term energy forecasting and very short-term, because when we speak about middle-term and long-term forecasting, we mostly deal with global meteorological models, which produce us with sort of mean assessments of the energy which can be produced by photovoltaic. And this information can be used for strategic planning. And the goal of our work was to find the solution, the reliable solution, to provide our system operator, power system operator, with the tool to produce the forecast of power system operation mode for tomorrow and for intraday planning. Moreover, so we produce some recommendations in terms of power system reserve capacities, because when we have a big share of renewable energy sources, there is a very big need of extra reserve capacities, thermal plant reserve capacities, which cover the fluctuations of solar power plants output. So we've developed the methodology which was built on risk approach, which gives us the idea of the risk of the balance deviation in the power system, and provides us with certain measures to be taken to eliminate this disbalance and ensure reliable operation of the power system. Well, if coming back to business in terms of the short-term scenario of photovoltaic plants forecasting, so this diagram gives a very general idea. Of course, we have some input data which is somehow processed and it's been prone to filtration. But we have some adjacent power system parameters. It's like power transmission lines, power transformers. So we have to ensure that our photovoltaic power plant is able to produce all of the power which can be extracted from solar irradiation. We have some weather data. There is an external data source, and this data is extracted from weather providers, which produce us with the forecasts for day ahead and for hour ahead perspective. And they give us the values of clouds, the temperature, the pressure, the humidity, and other factors. Some of the weather providers produce linguistic variables like cloudy, partly cloudy, or maybe foggy. And so we have geographical data. It's very important because the geographical data actually gives us the pivot point, which can be used to calculate the basic possible solar irradiation for this geographical region. We have weather monitoring system data. This system is installed at the power plant facility, and it gives us again the ambient temperature, pressure, humidity, and solar irradiation, because we have a horizontally installed pyranometer, and this data is very useful for us to produce the intra-day forecasting and intra-hour forecasting. It makes it very accurate. So, and of course, we have power equipment passport data in terms of inverters, converters, PV panels. Sometimes PV panels are quite different because there can be different panels installed at one power plant facility. So, and this should be taken into account also. Then we produce the forecast of solar irradiation. And based on the forecast of solar irradiation, we produce the forecast of solar power plant output. And this makes us a two-stage procedure. And this two-stage procedure gives us some extra flexibility, because the second model, which calculates solar power plant output, is mainly electrical. And in electrical model, we can take into account the state of the panels, the state of the inverters, because some of the equipment can be put out of the operation for repair and maintenance for some reason, and we may have some, let's call it, constraints from our system operator, and all of these features are to be taken into account in the second part of the system. But from my point of view, personally, the most interesting is the first one, because it provides us with the opportunity to produce a forecast of solar irradiation based on the weather data, which is extracted from external weather providers. Yeah, so this slide gives us a very general idea of the mathematical approach which was used to produce solar irradiation forecast. And so we used the so-called transparency index of the atmosphere, which gives us the relation between the solar irradiation which comes to the atmosphere and which is measured at the horizontal surface at the Earth. Yes, and the transparency index of the atmosphere is always between 0 and 1, where 1 is the ideal case, but we can never reach the ideal case because we always have some clouds, we always have some water molecules, which extract some energy from solar energy from the irradiation rays. But in the majority of cases, the weather is sunny, and we can provide a very reliable forecast. So, of course, one of the pivot points of the algorithm is the calculation of the irradiance at the border of the atmosphere, because it is the basic value which is subsequently multiplied by the transparency index. So it is the way we can get the value of solar irradiance at the surface of the Earth. We use multi-regression analysis, and I'll tell you a little bit about the history of this mathematical model, because this model was provided for the industrial company to provide forecasting of power system operation mode, and we had several iterations, and by improving the model with the initial data sets, the model itself, and so on and so forth. But actually, it was the first version the model looked like, and it was implemented in the industrial software. So you can see here the screenshot of this software, and I will give you a brief description of the application of this software, like first results of the application of this software in real operation conditions. Actually, this soft was tested on a real power plant, which was installed in southern region of our country. And well, we had actually 2-year initial data set, and the data had 1 hour resolution. Sometimes we got half-hour resolution, not more, but here we see the result of the sunny day forecasting. Actually, the sunny day forecasting is quite reliable for all of the possible versions of the model, because it is mostly based on the value of the solar irradiance at the border of the atmosphere. So we get some mean transparency index and produce the forecast for a sunny day quite reliably. And here we see the results for 20th of September of 2017, and the total output forecast of energy was produced to be 86,000 of kilowatt hours, and the actual value was 80,000 of kilowatt hours. So the second case study is the partly cloudy day. Well, this condition is quite more complicated because we have some characteristics of clouds for this day. And actually, if we look at the screenshot, at the lower part, forgive me, it's in Russian, but we see the graph of the clouds, yes? So, and the orange one is the actual value of the clouds, and the yellow one is the forecasted value of the clouds, because we know we have the data of actual clouds, which is provided by the weather provider as it is. So if this hour passes, so we can use this data and say it's actual data. But we have some forecasts, and the forecasts are updated each hour. It means that if we produce a day-ahead forecast, for example, after 24 hours, we will have 24 forecasts of clouds for each specific hour. And actually, we calculate the mean value of the clouds, yes, and make a sort of the forecast for our system too. Well, quite from this figure, it can be seen that forecast is still reliable, and we can use it for power system operation. The next case study is cloudy conditions. So again, we see the cloudy graph at the bottom side of the screenshot. The orange one is the actual value, and the yellow one is the forecasted value. So we see that situation is a little bit more tricky from the point of view of the accuracy of the forecasting, but from the point of view of the energy market, again, let's say it in terms of electrical energy production. So actually it almost matches, and the actual forecast, the actual value of the energy production was about 30,000 of kilowatt hours. And we forecasted 30,000 of kilowatt hours. Well, but there are some days, we'll call it extremely noisy days, which produced us with a very unreliable forecast. And so there were some measures taken to cope with this problem, because firstly, let's speak about the possible reasons of this problem occurrence, because there are some cloudy and rainy days which cannot be forecasted accurately. From one point of view, it's not too much important, because if we have a rainy or maybe a snowy day, it means for us that maximum possible power production of photovoltaic power plant is very low. So, for example, if we look at this figure, for example, this power plant has 15 megawatts of installed capacity. So theoretically, it can produce 15 megawatts. But for this day, so it produces only 1 megawatt. It's a very small share, and it can be negligible in some cases from the point of view of power system operation mode planning. But we produce the forecast of 3 megawatts. So the error is significant, but the total share for the power system is not too much significant. Anyway, we had to cope with this problem. And firstly, we tried to identify the reasons. So what's the reason? Of course, in the majority of cases, the reason is the noisy data. We used different forecasts from different weather providers, and different providers, first of all, they use different prediction models of the weather. I mean, numerical weather forecast models. It's first point. The second point, different models have different resolutions. And in the majority of cases, the models which produce free forecasts for the internet, they have resolution. I mean, the cell, of prediction is 100 kilometers versus 100 kilometers. So it's a very big point, and it means for us that for a cell having width and height of 100 kilometers, will have a similar weather forecast. But this territory is quite big, the area is big, and the weather can differ greatly. And if we see the conditions, the geographical position of our photovoltaic power plant on the map, we will see here that actually the the nearest meteorological station, it is located in the airport, is 45 kilometers from the photovoltaic power plant. So we have some sort of source of error in our weather data forecast. It's first point. The second point, actually, it's different weather providers produce different data in terms of the type. Because let's say Yandex Weather produce cloudiness forecast in percentage, when Weather Underground weather provider produces cloudiness forecasts with the figure and with linguistic description like foggy, rainy, partly cloudy, and some other characteristics. There are above 20 possible characteristics which can be used. But it's quite complicated to process these characteristics because we need to make a sort of the scale of factors and take into account these linguistic variables too. On this slide we see the algorithm bottlenecks, but mainly it's not the algorithm bottlenecks but the initial data bottlenecks. When we compare let's call it different cases with different noise scenarios. For example, the case 1, which is showed on the left side of the slide, is characterized by the following. The first, the left one, so it's given for 95% of clouds, but about 500 watts of insolation. But if we consider the right part of the figure, so we see that clouds of 50% have the irradiation of 170. But from logical point of view, it should be vice versa, yeah. And but for this scenario, the greater cloudiness corresponds to the greater radiation. So, and this provides us with a very noisy case of PV power plant forecasting. At the right side of the slide, we see the second case. It's when irradiation of 500 watts per square meter is observed when the clouds are 80%, but irradiation of 80 watts per square meter is observed when the clouds are 95%. The difference is very small in terms of the cloudiness coverage, but the amount of irradiation which was measured by the pyranometer differs dramatically. It's 5 times different. And this scenario actually means that there is a certain lack of features in the initial data which can give us some extra useful information to characterize particular weather conditions. And the first thing we made to eliminate these bad days forecasts is the clusterization of initial data. So on this slide we see the characteristics of the initial data set, of the 2-year initial data set produced for our photovoltaic power plant. And we see different times of the day. It's like morning, evening, before and afternoon, the noon time. And on the vertical axis, we see the transparency index, and horizontal axis corresponds to the cloudiness. It can be easily seen that different cloudy conditions are characterized by very big, wide range of transparency index. For example, for morning, evening, the cloudiness of 50% corresponds to the range of transparency indexes starting from 0 to 0.9. Actually, it's a very wide range, which means that we require some extra feature or data clusterization to provide more reliable forecast. So what have we done? We have used K-means dataset clusterization to produce some useful clusters characterizing one or another climatic and weather conditions. So on these slides provides us with the step-by-step procedure of producing the clusters of initial data set. And we had some initial clusters, then we had iteration 1, 2, 3, 4. And finally, we've come up to the following clusters of the initial data. So we have the following features used in our algorithm. It's solar altitude angle. Actually, it can be said that it's the height of the sun at the horizontal plane. Then we have cloudiness in percentage, and then we have sun declination angle. It's seasonal characteristics of the sun. And this produces us with the following clusters. For solar altitude angle, it's morning-evening value. It's close to morning-evening value, some transient values, then close to noon and noon. Then for cloudiness, we have almost sunny, low clouds, middle and high clouds. And for seasons, we have winter and summer, but we do not have spring or autumn because in our case, it's mainly off-season period because the weather is highly unstable. And this time, mainly starting from February till May in spring, is characterized by extremely stochastic weather. And in autumn, it typically starts from September till November, when the weather fluctuates, and we are really challenged to produce a reliable forecast. So, and actually, the clusters gave us the possibility to provide some filtration because we've calculated some dispersion and standard deviations for each of the cluster, and we have eliminated some runouts which were initially given in the initial data set. Well, and after that, it provided us a much more pleasant picture because we had the determination index of 0.88, when in the previous case, yes, so we had 0.65, which gives us the opportunity to produce much more reliable photovoltaic power plant forecasting. Yeah, and actually this is the example of the PV power plant production forecasts. In orange columns, we see the actual data. Then we see the predicted data using multiple regression and the predicted data with the dotted line with multiple regression improved by pipelining. So, and the final result, the mean result of the forecasts was about 90%. And actually, it suits our system operator in terms of power system operation planning, because when power system operation planning is carried out, we typically take 20% reserve for uneven fluctuations of electrical load and fluctuations of renewable energy production. Yeah, and as I have already said, this mathematical approach was implemented in industrial software of ProSoft systems. And actually, we have the error less than 6% for day-ahead forecast in approximately 80% of cases, and error not exceeding 13% in 92% of cases, which provides us with a quite valuable result. Well, the second problem that we were dealing with is the very short-term forecasting, because the system operator provides each hour, it provides the update of the electrical load forecast. And in terms of the development of renewable energy sources, so it has to provide the update of renewable energy production forecast. And we have taken the problem of very short-term forecasting, and the main, let's call it the core perspective is 1 hour ahead, but it can produce forecasts for 6 hours ahead with quite attractive accuracy. And sorry for this. What we have used in our model, so we use the algorithm of extreme gradient boosting trees, and we implemented this model in Python. But there are some extra data which should be taken into account when compared with the algorithm implemented for day-ahead forecasting. Actually, when we use intraday forecasting, when we take intraday forecasting, so we have some extra data which can be useful for us to adjust the short-term forecast and to make it more reliable. One of these types of the data is the measured transparency index, because we have the horizontally installed pyranometer on our photovoltaic power plant, and it provides us with online measurements of the solar irradiation. So we can use this reliable data to adjust our forecast for 1 hour ahead perspective. Moreover, to make our forecast more reliable, so we introduced another feature into very short-term forecasting model. So we introduce the short-term forecast value. So if we have a short-term forecast value and the measured transparency index, the algorithm tries to find the equilibrium between the produced short-term forecast and the actual irradiation to minimize the total error of 1 hour ahead forecasting. And we have 3 different input data sets. The first one, we call it learning without history. Actually, from point of view of taking into account the weather conditions, it's absolutely meaningless. But we have faced some extreme situations when the internet connection failed and the weather forecasting data cannot be extracted from the database of the weather provider, and we do not have weather forecasts of the clouds, of the temperature, of the humidity. So what shall we do now? And for this reason, learning without history model do exists, because it produces us with the forecast of the sunny day. So it does not take into account the history, it doesn't take into account meteorological data, but it produces us the mostly physically viable solution when we do not have the required data in terms of the weather and online monitoring systems. The second case study is learning with history, when we have measured transparency index and short-term forecasts. And the final case is learning with history and actual meteorological data, which is extracted from the database of the weather provider. Yes, as I have already said, we use gradient boosting trees. Gradient boosting trees provides us a very powerful tool because it belongs to the class of the ensemble algorithms, and the trees in the ensemble vote for the best solution, and actually each subsequent tree for the gradient boosting trees algorithms provides us with the solution minimizing the error of the previously obtained decision tree. And we have tested this problem and get very pleasant results, because now we have for 1 hour ahead perspective, we have the accuracy of 97%, and in 92% of cases the error does not exceed 7% of the installed capacity of the solar power plant. And if we give a little bit more attention to this diagram, we can see some very interesting problems dealing with the initial data, because the red line gives us the idea of the data which characterizes the cloudiness. It's the cloud coverage, which is expressed in percentage. The axis is the right one. And we see that the short-term forecast, which was produced for the day-ahead perspective, it is the orange columns. Actually, they strictly follow the value of the clouds. Yes, and when the cloudiness grows, the forecast of the produced energy decreases. But we see that the actual data gives us quite another result, because we do not have a severe reduction of the energy production when we have the cloudy conditions. But this drawback introduced by short-term forecasting algorithm can be easily caught by very short-term forecasting when introducing current measurement data. Yes, and one of the important things that I have to say about is the application sphere. Of course, well, some of my colleagues from my university say that I'm rather a meteorologist, yes, rather than the electrical engineer, but I'm certainly an electrical engineer, and I deal the problem of PV power plant forecasting in application to power industry. And one of the goals of the research work was to produce a model which could provide us with a certain knowledge of the energy produced by renewable energy sources to optimize the spinning reserves of the power system. Because nowadays, actually, without the instruments of renewable energy sources forecasting, the installed capacity of solar and wind power plants, they are completely taken into account in reserve capacities. And in case of the United Power System of Russia, so if we have 1 gigawatt of installed capacity of renewable energy sources, we have 1 gigawatt of extra reserve capacities, but it's not effective from the point of view of the energy market because it is, let's call it, highly efficient thermal power plants or hydropower plants, ensuring very fast regulation. But in the majority of cases, the reserves in the amount of the installed capacity of renewable energy are not required. And we introduced a methodology which gives us the idea of the risk of balance deviation in the power system. And actually, it gives us the result of measures, what should be taken to eliminate this imbalance in the power system and come it back to the initial state. And this slide provides quite a theoretical example, but it can be compared with the big industrial region of our power system. And so let's assume we have 1,000 of megawatts of combined heat and power production and 50 megawatts of photovoltaic energy are introduced into the power system. So, and we finally produce the risk distribution curves. And when the photovoltaic power plant is introduced, the risks of imbalance is increased by 5%. Yes, and let's fix that photovoltaic installed capacity is 50 megawatts. But in order to eliminate the risk of the imbalance of the power system, we are to introduce only 7 megawatts of extra reserve capacities, not 50 megawatts, only 7, to put the risks to the initial value when we had the share of the power system without photovoltaic generation. And of course, it can only be applied if the certain forecasting procedure is introduced, because we made a very big amount of forecasts, and finally we've got the statistical distribution of the forecasting error for day ahead and intraday perspective. And having the statistical characteristics of the error distribution, we are able to find the value of possible risk and the value of the active power which is needed to be introduced to eliminate this risk. Well, actually, in terms of the meaning part of my presentation, that's all, but I'd like to introduce the project team. Of course, firstly, it's me, but last but not the least person in the project is my colleague. She's Alexandra Khalisma. She's the associate professor of our university too, and she works with me in the sphere of renewable energy sources forecasting. And well, it's like an acknowledgement page for me, and her role in the project is very, very significant for the research work too. Some information should be given about the project support, actually, because this project takes its roots in the international grant which we are still participating in terms of the European Union. We have a consortium of 10 universities, and there are universities from Russia, universities from Vietnam, and 3 universities from Europe. We are producing the educational program of smart energy systems in Russian and Vietnamese universities, which will be implemented, I hope, in 2021 in all of the universities of the consortium. And one of the interesting parts of the project is the course, the discipline, Artificial Intelligence and Machine Learning in Smart Energy Systems, and the problem of renewable energy source integration in terms of the application of machine learning and artificial intelligence is a very important share of this course and discipline. And for this reason, it relates to the project and is developed within the framework of the project too. For this topic, I mean the topic of machine learning in power system, so we have the internship in Ural Federal University. So we have the corresponding associated partners of the internship. These are the main, the leading industrial partners and companies of our university in the sphere of power and energy. And some famous companies like Gazprom and Russian Grids, Rosseti, and Swell. It is the producer of power transformers. And the Prosoft Systems Corporation, it's the corporation which produced industrial automation, and it was the first company really interested in the development of the program software tools to produce renewable energy source forecasting. So we'd like to thank our university for the opportunity to share our knowledge with our partners and our friends from other international universities. And it's my great gratitude to our International Education Programs Department, because it's there recently that we introduced the course of Machine Learning and Artificial Intelligence in Summer School University for the students coming from Indian universities and from French universities. And I'd like to share some very good experience of collaboration with Bharat University of India, because the students coming from that university, from the summer school, and the academia from that university, after the summer school, we've made a sort of the collaborative project, and now we are producing scientific projects and improve the results which were obtained during the project of renewable energy sources forecasting. And now we have submitted an IEEE transactions paper, and I think it's a very important scientific results for us as a professor, staff, and for the students too. Well, that's all for me. It was a great pleasure to introduce myself and the topic of my research. Thank you for the floor, and if there are any questions, I would love to answer them. So thank you very much for your attention.
Thank you, sir. Now moving on.
In the chat section, and thanks to operation, yes, a well-taken scientific research. Yeah, so I have one remark that countries with multiple seasons need accurate forecasts for solar utilization. It's true actually, because we have some solar power plants allocated in different regions of the country, and even we have a solar power plant allocated in Yakutsk, and it's a far northern part of our country, and it could be up to, let's call it, -60 degrees in winter, and actually it is not efficient. I think it's not efficient in winter because there are some polar nights, and during the polar nights the solar power energy is not produced. But the summertime for the northern regions of our country are typically very hot, and they have very long days, and for this reason there is a very big share of diffused solar radiation, and they produce a huge amount of electrical energy. And it could be should be very carefully addressed for different regions. It's true. Yes. Please give your opinion on hybrid wind battery systems. Actually, we had some experience of hybrid battery systems, and there are some colleagues from other Russian universities working with us on that matter. And we've calculated hybrid battery systems for different regions too. And I think, well, it's effective, but it depends. It depends greatly upon the conditions, because we have to address very carefully the energetic potential of wind energy or maybe solar energy to use it with the battery. And it's the first point. And the second point, we have to very accurately address the sphere of application of our system. So what for are we going to use the wind and the battery? So if we are going to use it for standalone operation, just to cover the energy demand of the separate power system, maybe small power system or region, yeah, so it's one case. But when we consider, for example, the reserve capacities, it could be used as a backup source of power supply. It's another case. And for example, in our case, we have calculated the case for the far north region when there is a network connection of the load, but the network connection sometimes, well, not sometimes, but often fails due to the distance, because it was about 60 kilometers of 10 kilovolts power transmission lines, and there are forests, swamps, and very hard to access territories. And the period of service and maintenance is very big too. So, and once it was a New Year failure, and it was 11 days of recovery of the power supply. And we suggested the application of hybrid wind battery systems to provide the energy backup for the period of the energy shortage. And I think it depends on the conditions. And first thing we are to think about is the sphere of application and the energetic potential of the energy source that we are going to use. What kind of machine learning algorithms have you applied in condition of monitoring of transformer? Well, yeah, I know the answer. Actually, it's quite out of the scope of my today's presentation, but anyway, in terms of the condition monitoring of the power transformer, we used several approaches of machine learning. Firstly, we made it using, let's call it fuzzy neural interference. And now we are using extreme gradient boosting trees too. And actually now we have found out that the gradient boosting approach outperformed the fuzzy one, because you know, the fuzzy logic approaches, they require a lot of manual labor. Yeah, so we have to provide some membership functions, some rules. We have to do it expertly, and to provide all of these conditions for our system. And firstly, it's very time consuming for the operator of the software tool. Well, secondly, it's at least at initial stages, it gives us a very significant error in power equipment state estimation. So gradient boosting trees in this case outperform. So we use, so now we are working on other transformer monitoring approaches, and other equipment approaches too, actually, because if we do not consider a power transformer, or maybe we consider a circuit breaker, it's another case and it's another model, because it's a very important power equipment unit too, and technical state estimation of a circuit breaker is carried out according to the national legal documentation. But there are no tools, I mean software tools, that produce state estimation of circuit breakers. And there are very interesting features that can be taken into account in circuit breakers. For example, like short circuit currents. The calculated values of short circuits can be used to improve the assessment of circuit breaker technical state. Actually, it's the topic mainly of Alexandra. If you are interested, so you can email me and I'll give you her contacts, and she'll share her knowledge and achievements in this sphere. Well, will future big data database supported by artificial intelligence be used in precise forecasting in order to verify futurological projections? Well, it's a very interesting question, actually. In terms of precise forecasting to verify future projections, let's call it, if dealing with the project of renewable energy source forecasting, at the moment, we do not have a database which can be called big data, because we have some historical databases of a couple of photovoltaic power plants allocated to different regions of our country, operated for 5 years. And well, let's say 5 years and 1 hour resolution of data, it gives us about 50,000 of data samples, but it's not too much for processing. But anyway, when moving forward to big data databases supported by artificial intelligence, I think some other approaches can be used to provide the problem solution, like deep learning approaches, which are well, required to be further investigated in this case. Is there any disturbance in grid due to the solar rooftop system in generation of power plant? Well, actually, yes, but it depends again. So when we consider the global process of installing the rooftop photovoltaic power plants, there are some issues which should be taken into account very carefully. The first issue is the grid one. Because initially power grid is designed to provide efficient power flow for the final customer. So let's assume you have the peak energy load of, let's call it 5 kilowatts, for example, and you have the corresponding power network facilities, which gives you the opportunity to consume these 5 kilowatts from the external power network. But when you install your own generation source, for example, the photovoltaic one, so you produce the unload, yes, of the external network, and it's good from one point of view, because well, there are no severe and overloading conditions of the external network. But from the other point of view, the economical point of view, the grid company suffers from these measures, because they lose the useful output of their network, but they still have to provide maintenance and service for the power transmission lines, which were initially designed for the full load. It's a little bit the problem of the economic sphere, because from my point of view, it's a little unfair, because the power network is designed to cope with the peak loads, but the peak loads are not required, and the grid company has to provide service and maintenance of the grid facilities. It's the first point. And the second point deals with security, because when we have some disconnections in the external network, we have to ensure the secure operation of the engineering staff of the power network company, which provides maintenance and service of the power transmission lines. But if the grid company doesn't know that you have your own generation source that produces a certain amount of voltage, yes, so it produces a threat for the operation personnel working on the power transmission line in terms of recovery and maintenance. And anyway, this process can be regulated somehow, I think, but it is the problem of power system operation personnel security too. And the third point actually is the balance point. I mean the balance of consumption and production of electrical energy. There are some countries, for example, like our, where the rooftop power generation are not so popular, and it does not produce any threat for power system operation mode. But if we take a certain share of the photovoltaic power plants covering the load, let's call it 20% or maybe 30% of load, so it can produce some problems in terms of the operation and control, which can be coped with by using adaptive methods, information, telecommunication systems, and the corresponding machine learning approaches in terms of the control, reliability, and security of the power system. Well, is there a way to increase intensity of solar radiation on a photovoltaic cell, like magnified focusing? Well, I think actually there are such ways, but the most efficient way for a personal use application, let's call it, is to keep the surface of the photovoltaic panel clean. Is the first measure to be taken. The second measure to be taken is maybe to find the optimal angle towards the sun rays. So if you do not have a solar tracker which follows the sun, so there is a certain calculation algorithm which gives you the idea how to select the optimal angle of installing the solar panel to produce more energy. And finally, if you are able to provide some cooling environment for a photovoltaic power plant, maybe some windy conditions on the rooftop, it's quite valuable too, because if you provide good cooling conditions for a photovoltaic panel, it gives you a very good efficiency characteristics. How can we check the feasibility of solar predictor model? Well, actually, I did not get the idea of the question, because what is the feasibility of solar predictor model? And in terms of the feasibility, there should be some feasibility criteria, because when we speak, for example, about the electrical load forecasting, the feasibility criteria is the forecasting error again, but the, let's call it, top value of this error is very low. Nowadays, Russian power system produces the electrical load forecasting with the error not exceeding 0.5%. Yes, but when we produce the forecast of renewable energy sources, so we cannot ensure the forecasting accuracy of 1% or maybe 0.5%. And for this reason, actually, we are to check ourselves with the feasibility criteria. So what are the feasibility criteria? And in our case, feasibility criteria were the, let's call it, elimination of 20% errors of solar power plant forecasting. And it was reached. For this reason, we say that the solar predictor model is feasible. And maybe for some other power systems, there are some other constraints or limitations, and they should be treated differently. And maybe for this reason, we should introduce some improvements or other mathematical methodologies to make this model feasible. One of the points which should be taken into account, actually, so when we speak about solar power plants, we cannot calculate the error, the forecasting error related to the installed capacity of the solar power plant, because the installed capacity is constant and it is not changing throughout the time. But if we consider the maximum theoretically possible amount of electrical energy produced by a solar power plant for each hour, it differs. And there are, well, very few hours which can provide our solar power plant with the opportunity to produce the installed capacity. And for example, if we consider the morning or evening conditions, we can produce only, let's say, 10, maybe 20% of the installed capacity, but it is theoretically maximum value, and we cannot produce more in any conditions. And it does not mean, it does mean that we are to check the prediction error not with the installed capacity value, but the value of the maximum theoretically possible power produced by a solar power plant for a certain hour. It's a sort of the trick, but it's very logical, because it produces us with the physics of the process of electrical energy production from photovoltaic power plants. Yeah, so can you please guide us on synchrophasers? Actually, I think that this question lies a little bit outside the scope of the presentation, because it's very urgent, actually, but a problem dealing with power system operation mode calculations. So then I pass to the second question. The equipment is to be used in ideal temperatures, but in countries like India and the ones near equator have higher temperatures, and there are ways to still get optimum outputs. Yes, actually, if we take into account the international standards regarding the process of design of solar power plants, there are some recommendations which deal with the power plant design process. So firstly, we have to select the site of solar power plant location, and when we select the site, the area, so there are very big amount of criteria which would be taken into account. First of all, it's the price of the earth, yeah, let's say. It's very, typically it's very high. Secondly, so it's the potential of solar energy. Well, in Russia, it's quite urgent question, because there are not too much territory with high potential of solar energy. Maybe for India, there is a little bit another situation, but in this case, you have to consider the areas with the highest winds. So, and if you have high wind conditions, it provides natural cooling of photovoltaic panels and semiconductor devices, making them work more efficient. And there are some constructions, I mean, the structures, the steel structures used for photovoltaic panels mounting, they have some certain modifications which ensure natural circulation of air, and thus providing us with more pleasant cooling conditions. So that's the case, actually. The wind is also have to be taken into account when designing solar power plants as well. What are the parameters used to forecast about solar energy? Well, in our model, firstly, we had lots of parameters which can be used to calculate. These parameters can be classified to separate classes. Yeah, one class of the parameters is the parameter that can be calculated. So we just use the laws of geometry. Yeah, so how the Earth moves around the sun and how the sun moves in the sky. So we use a complicated sinusoidal model. to get the maximum theoretically possible value of the photovoltaic energy, of the solar irradiation, which goes into the atmosphere. It's one share of initial data which is used. The second share of initial data is meteorological data, which is used to take into account current weather conditions. So in our case, we use, for solar irradiation forecasting, we use only clouds. But when we come to the step number 2 of the algorithm, if you remember, is the electrical part of the algorithm, we calculate the power output of each solar panel, and each solar panel output is calculated taking into account the humidity, the wind speed, and the ambient temperature. So, and practically we take into account all the parameters which are provided by weather companies at the internet. And the third share of data, the third class of data, is online data, which is extracted from the metering systems installed at the power plant itself. Firstly, it's online weather data, like online irradiation, online temperature, online wind speed. And secondly, it's online measurements of the electrical meters of the power produced by the solar power plant. What is exactly circular transparency index? Well, the transparency index used in the algorithm, actually it describes the relation of the solar irradiance at the border of the atmosphere, yes, before passing through the atmosphere, with the value of the solar irradiation measured by the pyranometer installed on the horizontal surface of the Earth. Thus, it takes into account the loss of energy of solar irradiation in the atmosphere layer. So it never gives us the unity value, because even for a very sunny day, we have some dust, some water molecules, some invisible clouds, yes, and but it can be around 0.995 for a sunny day. How load balances in wind energy grid? How load balanced in wind energy grid and solar energy? Well, if we speak about balancing of electrical loads in the renewable energy sources based power networks, we have to ensure some energy storage facilities. Firstly, it's very important. So it could be some hydroaccumulating plant, or maybe it could be some electrical storage. It's the first point. And the second point, to my opinion, there should be a certain share of thermal generation, which is controllable and provides us a certain value of frequency, a certain value of power output to balance the deviations of renewable energy sources and load, or, and of course, some electrical energy storage. How high the variation in the outputs of solar panel plant can be reduced in order to synchronize it with the power grid? Actually, there is no problems with synchronizations of solar power plant with the power grid, because you know that solar panel produces the power at direct current, and then we use some converters and inverters producing a certain value of the power output at a given frequency. Yes, and for this reason, I don't think that the variation of the output of solar power plants somehow influences the synchronization with the power network. But in terms of the balance and power system operation mode, it plays a very important role, because there are some, let's call it, practical examples, yeah, when we had some energy districts isolated from the power system after the failure and the emergency. And these regions were supplied only by photovoltaic power plants. Actually, I haven't seen the measurements of frequency in this power system, but I know that solar power plants produced energy at a very low frequency. Anyway, they produced somehow. But anyway, there is no problem of synchronization of power network, of the power plant with the power network. Well, if there are no questions, let me thank you again for the question session and for the opportunity to speak. And thank you very much. It was my greatest pleasure.
Okay. Thank you so much, sir. Hello, everyone. I'm Pasha, treasurer at IEEE BVM student branch. First of all, I would like to thank Mr. Stanislav Eroshenko, sir, for giving his valuable time to deliver such a great and informative session on machine learning for solar energy forecasting and taking us through the topic from a basic to an intermediate level. I'm sure it will help many of our curious minds present here. So, we definitely look forward to have you with us in the near future. Thank you for your sharing. Thank you for sharing your knowledge.
Thank you very much. Thank you.
Now, I would like to call Dr. Kaushika Patel, ma'am, Associate Dean, International Collaboration Program, to say a few words.
Hello. Parth, am I audible?
Yes, ma'am.
Am I audible to you?
Yes, ma'am.
And visible too?
Yeah.
Okay, fine. Thank you. Good evening to one and all present over here. I'm Dr. Kaushika Patel, Associate Dean, International Collaboration for BVM. Our students do come to Ural Federal for summer schools, and their experiences at their university is excellent over there. We would like to have more research collaboration for faculties and students as well. We surely are looking forward for that. With that, first of all, I would like to thank Mr. Stanislav Eroshenko for the informative session on machine learning for solar energy forecasting in the era of the renewable energy. It will surely helpful to everyone to learn something new. Actually, I need to say special thanks to Professor Yana, Director International Relations for academic collaboration and speakers provision. I would like to thank our Principal Dr. Indrajit Patel sir for supporting us in all the sense. I also thank Dr. Darshan Dalwari, Branch Counselor, IEEE BVM, and our host Himanshu Thakkar along with his moderator team, Ibrahim Parth Shah, for handling the every session during the ITC 2020. I would like to thank the team IEEE BVM for organizing this event and all of the dear participants without whom we would not be able to spread the knowledge. I hope everyone enjoyed this session and will meet soon again in our next session, in the next session tomorrow. Stay safe and stay home. Thank you.
Thank you, ma'am. And before ending this session, I would like to remind everyone about our upcoming flagship event, Blogathon, a national level blog writing competition where the topic is not limited to only technical blogs, but you can also submit blogs written on the non-technical aspects of the world. And yes, why not? You can also write a blog about what you have learned from today's session and build your ideas on it. So kindly go ahead and register as soon as possible. Further details are given in the chat box. I once again thank you, sir, and thank you everyone for joining in. See you in the next session on Futuristic Radiation-Based Space Technology by Dr. Archana Sharma at 7:30 p.m. tomorrow. Thank you.